So while I was preparing the board, I asked you to evaluate Q transpose Q for this matrix over here, which I have copied nicely over here. And all of you did it correctly and said that it's the 3 by 3 identity matrix. Was it a coincidence? Of course not. Because when you're asked to evaluate A transpose B, if you think through the mechanics of matrix multiplication, one of those perspectives on matrix multiplication was called the dot product perspective. Am I right? Where you were to get the number in the result one at a time, one entry at a time, you would just dot the right column of B with the corresponding row of the matrix on the left. So you were dotting the columns of this matrix with the rows of this matrix. But if I put A transpose here, then the columns of A transpose, the rows of A transpose are the columns of A. So you just end up dotting the columns of A with the columns of B. That's another matrix notation, matrix expression for saying find a matrix that consists of pairwise dot products of the columns of A and B. Basically, multiply every column of A by every column of B and arrange them appropriately in the resulting square matrix. It doesn't have to be square. Whatever size it is, just the right number. Okay? Pairwise dot products of the columns of A and columns of B in matrix speak. That's the beauty of the matrix language. And that's what you're doing here. You're being asked to find pairwise dot products of the columns of a matrix whose columns are orthonormal. So of course you'll find zeros on the off diagonals and ones on the diagonal. Okay? So the columns of Q are orthonormal. So all of their dot products with each other but not themselves are zeros. That's these 6 zeros. And the dot product with itself is 1 in each case because the columns are orthonormal. So to say that the columns are orthonormal or to write down this are absolutely equivalent. So I'll bet you never done it. If you go on Wikipedia and look up orthogonal matrix, it'll have this as the definition, much more compact. Any matrix so that the transpose times the matrix equals the identity matrix is called orthogonal. It's equivalent, absolutely equivalent to stating that its columns are orthonormal. So not at all surprising. So now I will show you a magical aspect of an orthogonal matrix. Are you ready for it? And at first, I hope it will blow you away. And then you'll see a simple explanation for it. Let's start with this matrix, which I denoted by O, where I just put the vectors at the point where they were orthogonalized, but not normalized. So the columns of this matrix are orthogonal, but not orthonormal. You can kind of think of this little thing that makes it a wiggle, that makes it a Q, is that final normalization step. So this is short of that. So its columns are orthogonal, no doubt. What about its rows? Let's check. Are these two vectors orthogonal to each other? According to that same inner product? No, of course not. It's minus 12, not 0. Are these two? Okay, by accident. And these two are by accident also. It's because of the special values that I picked. But there is no reason to expect them to be. Why would they be? If the columns are orthogonal, what's the connection? That the rows will be orthogonal also. Nor are they normalized to unity at all. So the fact that there's some orthogonality in there is a total coincidence that I'm not too disappointed by. That can happen, but no reason to expect it to. Let's look at this matrix, which you might think is a little bit cumbersome because of the square roots, but it's totally worth it, the magic. Let's find out about these two rows. Are they orthogonal to each other? Let's see. I'll count in 25th, okay? Or maybe in 50th. It's better to count in 50th. This would be 24 50th minus 12 50th minus 12 50th. 0. These two rows are orthogonal. Why would they be? Just because the columns are orthonormal to each other. Why would? Okay, well, let's check the normalization. Is this guy unit length? I will once again count in 50th. I get 32 plus 9 plus 32 plus 9 plus 9. 50/50th. This row is unit length. Let's check this orthogonality. We'll count once again in tenth. That's what you want to do here, right? That you get 10 on the bottom naturally. So we'll count in tenth. 4 minus, well, it's obvious. What about this one and this one? Once again, obvious. Are they unit length? Look at this one. Is this row unit length? Yeah, I'm just milking this, savoring it. Are you guys amazed? I mean, with being orthogonal, just because columns are orthogonal, doesn't it all say anything about the rows? They're nothing. This O is for the second O in nothing. That matrix doesn't have any particularly special properties. But this one, my goodness, it has orthonormal rows. So orthonormal columns means orthonormal rows. And I'm enjoying it so much because I'm a geometry guy at heart. And this is pure algebra. It's just amazing. I don't know anything in geometry that sort of has the same. If it exists, it's artificial. It's because mathematicians realized this fact about matrices and artificially contrived some geometric configuration where that's also true. But I have zero doubt that this was discovered algebraic. It's a pure algebra fact. And algebra has its magic. And this is the magic. And who can explain it? You have a question or an explanation? Of course, yeah, and you will answer both questions. Yes, it goes both ways. Orthonormal rows means orthonormal columns. Orthonormal columns means orthonormal rows. Who can prove it? Who can explain why it's true? Very simple reason, but a divine reason nonetheless. Let me lead you up to it. Do matrices commute in a product? They do not. AB does not equal BA. But there is one very special, there are many, but one of them is very special exceptions. When the product equals the identity. In other words, when one of the matrices is the inverse of the other, then they do commute because they're each other's inverses. Or a math person would say because the right inverse is the left inverse. So AB typically is not BA. But when the result is the identity, then you can multiply them in the opposite order and still get the identity. That's what I refer to as a gift from God, because it's unimaginable if you look at it not from a more elevated point of view, but from the detailed point of view of how numbers, entries interact with each other when you multiply them together. Because when you put matrices in the opposite order, totally different entries interact with totally different entries to produce the same result. Miracle, which it's not. But it seems like a miracle. I think whenever you see magic, sleight of hand, it's not magic. It's just skill. But it's so much more enjoyable when it appears as magic. So it's the same thing here. Yes, I know the simple explanation for why if AB equals identity, that BA equals identity also. There's several very simple explanations. But that doesn't remove the magic. It's still magical. So that's what this is saying. So another way of saying orthogonal matrix is to say its inverse is the transpose. So orthogonal matrices are the easiest to invert. You just take the transpose. That's why people love orthogonal matrices. You just have to transpose it, which is very easy, to invert it, which is usually not. So the easiest inverses are for orthogonal matrices. It's right here. It is not its own inverse, but its transpose is the inverse. And so you can write this in opposite order. And what this is the dot product of the rows of Q with the columns of Q transpose. In other words, with the rows of Q. So if this says that columns of Q are orthonormal to each other, then this purely algebraically reversed identity tells us that the rows of Q are orthonormal to each other. So it's basically a throwback to the identity discussion and nothing else. Pure algebra. Did you see how there was a lot of geometry theory? Gram-Schmidt orthogonalization came from geometry. Inner product, orthogonality, lengths, all inspired by geometry. And all of a sudden there's a result that is just pure algebra. That's the power of combining the two subjects. And now I will mention one more fact about orthogonal matrices. I kind of want this magic to have more oomph, but I think I'm done with it. That's all I have to say about it. I will ask you, what's the determinant of an orthogonal matrix? We'll work with this one. I know you all did the right thing. You took the determinants of both sides. Correct? And then you remembered that the determinant of the product is the product of the individual determinants. Another one of those amazing things if you look at the details of what's going on, and such a basic fact if you look at the big picture. So this is how you do it. Right? And then you remembered that the determinant of the transpose is the same as the determinant of the matrix, so you just did this. And so you now know that the determinant of Q squared equals 1. And so if x squared equals 1, then what is x? Plus or minus 1. So the determinant of an orthogonal matrix is plus or minus 1.